You know that little feeling of panic you get when the power flickers? Well, it turns out there's this constant, invisible battle being fought with math, of all things, to keep our lights on. Today, we're going to pull back the curtain on the hidden mathematics that stop a blackout before it can even start.
All right, so let's start with a really simple question. What happens if a major power line just fails? Maybe it's a storm, maybe it's just old equipment. Well, all that electricity it was carrying has to go somewhere, right? It doesn't just vanish. It instantly floods all the neighboring lines looking for a new path. And if those lines can't handle that sudden surge, boom, they fail too. And that's how you get a chain reaction, a massive cascading blackout.
So, to stop that nightmare from ever happening, grid operators have this one golden rule they live by. It's called the N1 security principle. And the idea is actually pretty simple. The grid has to be built strong enough to lose any one thing, a power line, a generator, whatever, and just keep on running without a hitch. It really is like an invisible shield for our entire power system.
Sounds straightforward enough, doesn't it? Just build in some extra strength. But here's the catch. When you're trying to plan the grid of the future, one that's packed with unpredictable wind and solar power, that simple rule turns into an absolutely massive math problem. And we're not just talking about some abstract equation here. Solving this is the key to building a green energy future that's both reliable and affordable.
I mean, just try to wrap your head around what it would take to be 100% sure the grid is safe. First, you'd have to simulate what happens if every single power line fails, one by one. Then, you'd have to do that for every possible way power is being generated. What if it's super windy up north, but cloudy in the south, or the other way around? And you'd have to run all those scenarios for every single hour of the entire year. The numbers just get insane.
And this really shows you just how much the complexity explodes. For a basic grid plan, the number of rules or constraints you have to follow is roughly 2 times the number of power lines. Let's call that 2L. But if you want to make it fully N1 secure, that number jumps to about 2 times the number of lines squared. We're not talking about a small step up. This is a gigantic exponential leap. And the end result? Well, the researchers put it perfectly. It's a computational nightmare. Seriously, it's not just a tough problem. Trying to run these numbers for an entire country's power grid, it's basically impossible. The most powerful computers we have just can't do it. Okay, so if just throwing computer power at it won't work, how do grid planners actually get anything done? Well, they use a really clever shortcut. It's this idea of creating a buffer zone for every power line.
The technical term is a heuristic, but really it's just a practical shortcut. Instead of trying to model every single possible failure, planners just build in a safety margin from the get-go. They basically pretend each power line is weaker than it actually is. By derating the capacity like this, they create this artificial buffer, some extra room to handle the shock if another line suddenly goes out. And this isn't just a theoretical idea, by the way. It's what the industry actually does. There's this common rule of thumb, which the paper points out, that you should never load a power line past 70% of its real capacity. That's its physical limit, how much it can handle before overheating. That leftover 30%, that's your buffer, that's the safety net, just sitting there in case something else in the grid fails. But that leads to the big question, right? Is 70% the magic number? I mean, it's just a good guess. Maybe it's way too cautious, and we're spending billions building a grid that's way stronger than it needs to be. Or maybe it's not cautious enough. And does it even make sense for a massive power line feeding a city to have the same buffer as a tiny one out in the country? These are the exact questions this research wanted to answer. All right, and this brings us to the really groundbreaking part of this whole thing, finding a way to actually calculate the perfect buffer instead of just guessing. Okay, let's get into this because it's a really cool way to visualize the problem. Imagine you could map out every single possible way to safely run the power grid. All those safe options would exist inside a complex geometric shape, a polytope. Now, the shape for a perfectly secure grid is super complicated, with all sorts of weird bumps and edges. The simple 70% rule creates a much simpler, smoother shape. So the whole game is to find a simple shape that does the best job of mimicking that complex, truly safe one. And this shows the 2 main ways they tried to do it. The first one is called the robust approach. See how it creates a smaller shape that fits completely inside the true safe zone? Anything you plan in there is 100% guaranteed to be safe. The downside? You might be missing out on some cheaper but still safe ways to run the grid. Then you have the approximate approach. This one tries to match the size of the original shape. It's a much better match on paper for saving money, but you can see parts of it poke outside the true safe zone, and that means risk. So this table just lays it all out.
You've got the robust approach, totally secure, but you pay more for it. Then there's the approximate approach. It's cheaper to model, but there's no guarantee it's safe. But then, the researchers came up with a third way, called line-specific. And the idea was, what if you could have the best of both worlds? What if you could have 100% security, but keep the cost down by giving every single power line its own unique, custom-made buffer?
So that's the theory. But how did these ideas actually hold up when they were tested on a real-world model of the German power grid? Let's check out the results. First things first, and this is the big one for any planner. Is this shortcut actually faster? And if it is, are we talking a little bit faster or a lot faster? Well, running the full computational nightmare model for their test case took 3,786 seconds. That's more than an hour on a supercomputer for just one scenario.
And how long did their shortcut take? Just 270 seconds. That's under 5 minutes. I mean, that is an absolute game changer. It's the difference between planning being impossible and it actually being something you can do.
Okay, but speed doesn't matter if the results are wrong. So what about the cost? This chart shows you the estimated annual cost of running the system. The super safe robust method, it was about 4% more expensive than the perfect model. A little too cautious. But now look at the line-specific one. It's also 100% safe, but it slashed that extra cost in half. It's only 2% more than the baseline. You're getting something that's almost as accurate as the perfect model, but, more than 10 times faster.
And what about that 70% rule of thumb we talked about? Well, get this. When the researchers ran their numbers to find the most economically ideal buffer, the number they got was 74%. Incredibly close. It turns out that old industry gut feeling was actually pretty darn good.
So let's just wrap this all up. What are the big takeaways? First, that 70% industry rule, it's a surprisingly good estimate if you're just looking at costs. But if you want a 100% security guarantee, you need to be more conservative, and that costs more. The real hero of the story here is that line-specific approach. It gives you the best of everything. It's totally secure, it's super fast to calculate, and it's way cheaper than a simple one-size-fits-all buffer. These are the kinds of smart shortcuts we absolutely need to plan the complex renewable power grids we're building for the future.
And all this leaves us with a final, really important question. As our energy grid gets more and more complex, we can't just keep throwing bigger computers at the problem. The solution has to be smarter math. So as we build the grid of tomorrow, are these kinds of clever shortcuts going to be the secret ingredient that keeps everything running, both reliably and affordably?